Okay, so this is Unit 2, Part 2, basically, or Part E is what we're calling it, but it's going to be part of the Part 2 test. So it's E and F are part of Part 2. We're going to spend a couple days on this guy. Describing position and transforming data. So percentile is probably something you've heard of. It's a method of determining position of a given data set. So if you did really well on one of the standardized tests, you might be in like the 98th percentile or something. And so that 98th percentile means that there were a value of 98% of the observation less than or equal to what you got. So that's our definition. Some other books go slightly different or other than AP, but AP says that percentage or lower got that score less than or equal to it. Here are 25 scores. There's a score of, on a 50-point test, there's a score of a 43. Wow, one person got a 12. It's rough. Okay, so 43. So where does that rank here? So count the number of scores that are less than or equal to 43. It'd be nice if we had a dot plot. That would be much easier to do that. I'm going to count the ones that are above 43. So 1, 2, 3, 4. So out of the 25 students, 4 students were above the score of 43, which means 21 students were a score of 43 or lower. So 21 out of 25. You would then get your calculator out if you needed to. 21 divided by 25 and gives you 84%. So that would be the 84th percentile, which means 84% of the scores were 43 or lower. Be careful with your language. So those are just a little nuance here. We don't say it's, some people like to say it's in the 84th percentile, but it's at the 84th percentile to be more precise. We want to be precise with our communication. Usually reported as whole numbers. So this one is interesting. So you might not have, this might not be intuitive. So if you had 50 out of 75 or 66.7%-ish there, so you don't round up, you don't round, you round down to the nearest percentile. So we want that number of scores or below. So if we said 67%, we wouldn't be quite telling the truth. You're not actually at 67% or below. You're below that, so you have to start at the lower value, if that makes sense. Yeah, a higher percentile isn't always a good thing. If it's cholesterol level, you don't really want to be at the 90. Oh, it's true. Here's a dot plot of 71 randomly selected water samples taken from homes in Michigan. Calculate the percentile for the water sample of a lead level of 9 ppbs. Interpret this value in the context of the problem. So percentile, so you're going to want to count. I would count the ones above 9. So there's 2 at 10, there's 1 at 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I count 11 of the 71. So there are 60 out of 71 below that. So I think you would do 60 divided by, divided by 71, which is 84 point something percent, which is the 84th percentile. Oh, wait, 59. Did I count something wrong? So 1, 2, 3, 4, 5, 6, 7. Oh, there's one out there. I didn't see that one outlier way out there. Oh my goodness. So it's one less. It's 59 divided by 71, which is 83.1. So it's 83 percentile, 83rd percentile. So it is at the 83rd percentile. So this is how they said it. So the water sample is at the 83rd percentile in the distribution level of lead level. About 83% of Flint dwellings tested had water samples with lead levels less than or equal to 9 ppbs. Flint is famous for having bad water a few years ago, so that's why I think that was used, that example. EPA regulations require action to be taken if the 90th percentile lead levels exceeds 15 ppbs. Oh, that's interesting. So they actually use percentiles in determining if a water is safe enough to use. So based on this, what action should have been taken? So based on these dates, data, dates. Okay, so should have been taken. So let's see. So 15 ppbs. So 15 ppbs is right there between 10 and 20. So there are 1, 2, 3, 4, 5, 6, 7, 8 values above. So out of the 71, that would be 71 minus 8. So there are 63 values that are at or below 15 ppbs. They're actually all below, but 63 divided by 71 is 88.7, 88th percentile. So if the 90th percentile exceeds that, so because 64 of the values are less than or equal to 18, the 90th percentile is 18 ppbs. This exceeds 15 ppbs, so action should have been taken. So I figured that out a little differently. I looked at 15 ppbs and I actually liked their way better. So what they did, this is better. I got to get back into percentile mode. So they did 0.9 times 71, right? Because that's going to be where the 90th percentile is. Oh, I like that, right? So 63.9. Because 64 of the values, so 63.9 out of 71, so 64, because 64 of the values are less than or equal to 18, the 90th percentile is 18 ppb. So 64, which means 7, 1, 2, 3, 4, 5, 6, 7. Yes, so 64 is that 18th right there. So that's where that dot is. So that's the closest we have to the, so since we have is 18, that exceeds 15 ppbs. My way, you couldn't really tell. You were kind of like, I don't get it. It's close, but it didn't make sense. This way makes a lot of sense. So you want to find the 90th percentile and work backwards from there. I found that the level and work backwards, and that was not a good plan. And sometimes we do that in math. We think about things differently, and it didn't quite make sense. This is something we use all the time. So this is a biggie. It's on the formula sheet. You don't have to memorize it, but it's something we use a lot. It's called a standardized score. So we say standardized score, we mean z-score, typically. And to find the z-score, you take the value, the data value that you have, minus the mean, divided by the standard deviation. And that's going to give us position. It's going to allow us to compare some numbers. We're going to learn a lot more about Z, but we're just starting with, it's just a way to kind of compare things to see if it's above the mean or below the mean by how many standard deviations is basically how it works. So back to the same data. Where does Emilio's 43 marked in red on the dot plot fall in the distribution? So let's just look at the distribution here. So 43 is the median is 38. The mean is 35. So this guy is better than average, right? So he's better than both the mean and the median. Q3, which is the 75 percentile, so to speak, right? 75% is 41.5. He's better than 75% of the students. So he's definitely between 75 and 100%, just looking at the distribution there. But we can do better than that, right? We can actually plug it into the formula for Z. This will give us a thing here. So we go the value of 43 minus the mean of 35.44 divided by the standard deviation. So notice when I was just kind of ballparking it, I was like, I wasn't using the standard deviation. So the Z-score uses standard deviation, and it's a very accurate measure here. So we get 0.862. So compared to his classmates, his Z-score is 0.862. So he's 0.862 standard deviations above the mean. He's almost 1 standard deviation above the mean. He's 0.862 standard deviations above the mean. That's what it says. His test score is 0.862 standard deviations above the mean. It's positive, so it's above the mean. It's definitely possible to get a negative z-score. That would mean your score is below the mean by a certain number of standard deviations. Calculate and interpret the z-score for the water sample from Leanne Walter's home, which has a lead level of 104. So 104, oh my goodness, this person has a really high lead level, which doesn't seem good. I don't think I would want to have an outlier in lead levels in my water. Okay, so you would plug it into the z-score formula, right? So you get 104 minus, and definitely when you're using a calculator, is probably, use control divide to get that fraction template so you can type it in like that. It's going to be very nice to use. So type it in 104 and you get 6.74. Oh my goodness, right? So the lead level for this person is 6.74 standard deviations above the mean. Anything more than 2 in stats, we go, that's getting really unusual. This is extremely unusual. Be sure to interpret the magnitude, the number of standard deviations, and the direction. So that's very important. So notice I said it was above 6.74 standard deviations above the mean. If it was negative, it would be below the mean. You have to talk about direction and the number of standard deviations when you interpret a z-score. This is what they said. The water sample from Leanne's home had a lead level of 6.74 standard deviations above the mean for all 71 homes. The lead level in a different home's water sample had a standardized score of negative 0.37. Find the lead level. Oh, so this is interesting. So now we say, okay, we don't know what the lead level was, but we know this person was 0.37 standard deviations below the mean. So we know that's the z-score there. That negative 0.37 is the z-score. Well, we know the mean and standard deviation, so this is just, plugging into a formula. If you want, and this is, stats is not a math class really, so you can do this. So a lot of folks use the solve command here. So menu, algebra, solve. And so you can just type in the equation, negative 0.37 equals control divide x minus 7.31 over 0.347. And then we have to put comma x. Don't forget that when you use this command, comma x, or whatever the variable is you're solving for, and it should solve it for that variable. You could also just multiply negative 0.37 by 14.347, add 7.31 to get your answer. It's not a hard equation to solve, but you're certainly welcome to use the calculator to solve that if you want to. So you get about 2 is what they rounded it to there. So 2 standard deviations above, so 2 is the lead level, right? So we have to remember what we're doing here. We started with the z-score, and we ended up with the value, or the data value there, which is 2. So that's the lead level. So you're looking at like that second tallest band, the third column from the right there, somewhere in there is that person's home. The home's water sample had a lead level of 2.0 ppbs. Jordan was 55 inches tall at age 9. The distribution of height for 9-year-old girls has a mean of 52.5 and a standard deviation of 2.5. It's so nice that we know the mean and standard deviations for both of these. So we want to find out who's taller, right? In regard to their sex and their age. So you can't compare them apples to apples. You don't say, well, because girls and boys have different, mean heights and different standard deviations for their height. Depends on their age. I mean, there's a lot of factors here, but so I guess these are specific to those ages because I imagine there's a lot of variation early on. Some people grow quickly and some don't. So I imagine that standard deviation gets smaller as you age is my guess there. I don't know. We'll see. I'm not sure actually about that. So who's taller? So you've got to use Z-score equations for both these guys, right, to standardize them. So so if you do the math, so Jordan is 55. That's what the data was, minus the mean for Jordan. For girls, it was 52.5 divided by 2.5. So Jordan is 1 standard deviation above the mean in height. Zane, when you do the Z-score, is 0.5 standard deviations above the mean for height. So Jordan is 1 standard deviation above the mean, while Zane is 0.5. And so you would want to make a comment that Jordan is taller relative to her gender and age, or when you're comparing it. So Jordan is taller relative to girls her age than Zane is relative to boys his age. So it's a very specific comparison there, but it's good. And we want to be able to compare unequal scales. This is actually really helpful. If you have an SAT score and ACT score, you want to compare them, which one's better, you can use stuff like this, right? So we're done with the lesson. Let's just try a few problems here and see if we can kind of handle these. So people are living longer now than any time in recorded history. Certainly is a blessing, but also a challenge for countries when they must adjust to the needs of their aging populations. One statistic important in the social scientists who study this phenomenon of life expectancy at birth, STEMplot shows the life expectancy at birth in a recent year for 41 countries in Central America, South America, and the Caribbean. So there's a nice STEM plot there. We learned about those last chapter, so we still are expected to know how to do those. Calculate the percentile for a country with a life expectancy of 78 years, so 78. So at or below. So I'm going to count the ones above that. So there are 1, 2, 3, 4, 5 countries above that. It says there are 41 countries. So 5 countries above, 41 minus 5 is 36. So 36 divided by 41 is 0.878, so 87th percentile. So this country is at the 87th percentile in the distribution of life expectancy at birth. Notice they're parroting back the question. They're saying the context of the question there. About 87% of the countries in Central America, South America, and the Caribbean have life expectancy at birth less than or equal to 78 years, which is true. Oops. Life expectancy at birth in Peru is at the 39th percentile. Okay, so how do I find 39th percentile here? So let's get our calculator out. See if we can do this similar to the other problem. So 0.39 times 41. So 15.99. So 16, basically. So 16 at or below. 1, 2, 3, 4. I'm counting from above. 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm at 1 now. 14, 15, 16. So I think 72 is where that's at. So because 16 of the values are less than or equal to 72, the 39th percentile is 72 years. A Peruvian newborn is expected to live 72 years. So that was the data. Summary statistics for this. So this is the same data, it's just we only have the summary statistics. So we have like the mean, standard deviation, stuff like that we might need for z-scores. Calculate and interpret the z-score for Peru, which has a life expectancy of 72 years. Okay, so get your calculator out. So we're going to calculate that. So I would do your fraction, 72 minus the mean of 73.415. Let's see if we can make a prediction. So 72 is below the mean. So I think this is going to be a negative z-score. When we do this, the standard deviation is 4.159. We get negative 0.34. So calculate, interpret. So Peru has a z-score of negative 0.34, which means their age is, life expectancy is negative 0.34 standard deviations below the mean. So it's less than the mean for all 41 countries. Oh, very nice. Okay, life expectancy for Panama has a standardized score of 0.62. How many years is a Panamanian newborn expected to live? So now we have the z-score, and we have to calculate the other thing. So again, I might consider the solve command. So 0.62 equals the fraction of x minus the mean, 73.415. Sometimes it's just easier to do this. 4.159, 159, comma x. Okay, comma x. Okay, 75.99. So what are we finding there? We were given a z-score, so we're not rounding this down. This is the expected life expectancy is 75.99, right? So life for a standardized score of how many years expected to live. I think I did not put the answer there, but it's 75.99 or about 76 years is the expected life expectancy. That's funny. I think I put the question there instead of the solution there. That would have been nice to have the solution. Okay. Competitive gaming is not just a hobby today, but it's become a real profession. Some gamers make more than $100,000 per year. Maybe I should become a gamer. The League Championship Series pits teams of 5 players against each other in the game of League of Legends. 2 ways to measure the value of a player are the amount of damage they cause and the amount of gold they earn. The table below has the mean and standard deviations of the damage per minute and the gold per minute rates for 41 LCS players in a recent year. One LCS player, Chime, had rates of, do you all know who Chime is? Had rates of 182 DPMs and 228 GPMs. Was Chime better at causing damage or earning gold relative to all LCS players? Justify your answer. Actually, it's kind of an interesting question, actually. So what's his secret? Evidently, Chime is a pretty good player. So is it because of his DPMs or his GPMs? Which one is he better at? So you can plug in, so 182 DPM. So this is for DPMs, you do the minus the mean of 477 divided by the standard deviation, you get negative 1.2. And then for ZPM, you do the same thing for those two. They have different means and standard deviations there. Chime is below average in both causing damage and earning gold. I really thought with a name like Chime, he would be like the best. So I'm a little disappointed here. But because a standardized score of negative 1.2 is greater than negative 1.6, Chime is better at causing damage than earning gold relative to all LCS players. So it adds up to determine which one he's better at compared to himself. Like which one is his strength, I guess, is what they're asking, right? So he's pretty good, but compared to some of these other elite players, maybe he's not as good.